So today it's reinforcement learning for natural language processing, and this is a rather hot topic. So you see a lot of papers on this nowadays, and I will try to explain kind of what's going on here in simple terms as possible. So I think I really like the blog that was kind of the required reading for this because it lays out things in a relatively easy to understand thing, but it has nothing to do with NLP. So I'll kind of focus on the things that will influence your building models for NLP this time. So reinforcement learning, just to recap, is learning where we have an environment, X. We have an ability to make actions, A. And then after we've made our actions, we get a reward. We could get a reward after every action, or we could get a reward only at the end of a long sequence of actions. In the example of Pong, X was our observed image, A was up or down, and R was our win and loss at the end of the game. So why would we want to use this for NLP? There are lots of different scenarios where people apply these models. And many of these scenarios are very different from the one that you would expect according to the typical reinforcement learning. That being said, there are typical reinforcement learning scenarios that kind of match the original definition of reinforcement learning. And one of them is, for example, a dialogue where we're talking for somebody for a long time. And then at the very end of the dialogue, we get some sort of reward. So an example would be you build an online chat agent that is basically giving people product support. And you ask them a whole bunch of questions, then you forward them to the appropriate help page that solves their problem. And then you come back and say, did this, so here's the page, does this solve your problem? And they say yes, and you get a reward. So this would be a very typical reinforcement learning setting within NLP. Another reason why people use these is we have something like latent variables where we decide a latent variable, then get a reward based on the configuration of that latent variable. So one example of this would be, let me see the next one. So one example of this would be, for example, let's say we have a model where we have a sentence like this, and then we use a parsing model, which I'll be talking about in a little bit, to get a parse tree of that sentence. And then based on this parse tree, we then make a prediction about something, maybe about the class of the sentence or something like this. In this case, the only thing we observe is the sentence, but we're also using the parse tree in making our decision. So this parse tree is a latent variable that we can use to kind of improve the accuracy of our model. And one thing that reinforcement learning has been used for is to do things like this. You can also use kind of standard structured prediction algorithms as well for these problems. Another thing that people have been using this for is when you have something like a sequence level error function. So an example would be BLUE score for translation. Another example would be F measure for named entity recognition or something like that, where you want to you don't just get an error for each tag, you get an error for multiple combinations of decisions. And this is another place where people have been using reinforcement learning algorithms to solve these problems. So, so this is something to remember. I'll revisit this later when I talk about when to use reinforcement learning and when to not. So just as a very brief recap of the reading, in case anybody had any questions while they were going through it. So the standard algorithm that a lot of people use nowadays for doing reinforcement learning is policy gradient. So for supervised learning, in contrast to reinforcement learning, in supervised learning we're given the correct decisions. So basically, we can calculate our log likelihood like this, where we calculate the probability of p of y given x, and then we use a negative log likelihood to optimize our model. So this is what we've been using for all of the models that we've been training so far. We just optimize over our sequence of decisions. In the context of reinforcement learning, this is also called imitation learning. So imitation learning is basically where you have a sequence of actions that you would like to do, and you have some teacher that's telling you which actions you should be doing. So imitation learning is not, there are other varieties of imitation learning, but this is one variety of imitation learning. So if you hear imitation learning, it's basically like reinforcement learning, except somebody is telling you what to do instead of letting you figure it out on your own. So now I'm going to gradually take some steps in the direction of the policy gradient method that will kind of explain its connection to maximum likelihood. So the first thing we can think about is something called self-training. So self-training, basically what we do is we take a sample, or we take the argmax according to the current model. And then based on this, we use this sample or the samples to maximize the likelihood. So instead of taking the likelihood with respect to the true output, we take the likelihood with respect to our sampled or argmaxed output. So what this is doing is we're asking the model what it thinks is the correct answer, then we're trying to improve the probability of this answer. So does this seem like a good idea? I see a lot of confused people, so maybe not. What are the potential problems with this? Yeah. Yeah, errors will keep on compounding. So this y hat is not going to be perfect, right? So you're taking this imperfect thing and you're trying to train your model to improve the probability of that imperfect, potentially imperfect thing. So that's an obvious problem with this self-training method. That being said, this can learn, especially if the accuracy of your model is relatively high. And the reason why is just if it makes fewer mistakes than it makes is correct, it can learn from the context in the easy cases and then generalize it to the harder cases. But you never know if this is going to work or not because there's a lot of conditions under which you need to be in order for this to work. There's one successful alternative called co-training. So this is actually something that was invented and used a lot by Tom Mitchell here at CMU. And basically the idea is you have two models. You ask both of the models what they think the answer is, and when they agree, you use that to update your models. So this is a little bit of a better idea, right? Because the models, when they agree, they'll probably be right, especially if they're very different models. So yeah.
So instead of taking argmax, if you were to do something like say beam search, to get a much better estimate, then use that to take.
Well, beam search is actually approximate argmax, right? So when I say argmax, I don't mean greedy search. I mean the actual.
So for something like which is not structured predictive, because models would make global decisions.
Right.
But suppose there is a global structure to make things. So can you use something else to improve your estimate?
I'm not entirely sure what you mean by that, but basically think of this argmax as being the actual ideal maximum probability solution, and then beam search is an approximation to that. So does that help answer the question? So this is another alternative that people use. And this is kind of like the ensembling version of self-training. So ensembling, combines together two models. This combines together two models and then learns from their outputs. Okay, so now we have two things that we kind of know the relationship between. And then where does policy gradient or reinforce stand in in contrast to this. So policy gradient and reinforce basically adds a term that scales the loss by the reward. So in the self-training loss, if you remember, in the self-training loss, we were taking the negative log likelihood of the sampled output. In policy gradient, we're taking the negative log likelihood loss of the sampled output, but we're multiplying it by the reward. So if we have an output A, B, C, and its reward is 0.1, we'll basically update 1/10 of how we would update when we were doing self-training. And if we have D, E, F on the next sentence, and that reward was 0.9, we'd update almost the same amount as if we were doing maximum likelihood training. So this is actually, it's super simple. The reason why people use this is because it's super simple. You're basically doing maximum likelihood training with only two extra steps. One extra step is that you take, you randomly sample an output from your model, and then the next step is that you evaluate whether that output is good. So here's a quiz. Under what conditions is this equal to maximum likelihood estimation? I heard a lot of people talk at the same time. What? When the reward is 1. Pretty close. That's very, very close. And anybody else?
If you get the right answer, then the reward will be 1, otherwise it will be 0.
Yeah, exactly. So when you get the right answer, the reward is 1, otherwise it's 0. So basically when you're using a 0-1 loss, which I talked about before, where you get a reward of 1 when the entire sequence is correct, the entire sequence of actions is correct, then this becomes maximum likelihood. So this is basically good when you would want to use reinforcement learning, or you would want to use this formulation when that's not the case, when you have a loss that's not the 0-1 loss, and instead has gradations, or when you have multiple answers, or something like this, or when you couldn't do maximum likelihood estimation at all, because you don't know your true sequence of actions. So in a typical reinforcement learning scenario, you don't know the true sequence of actions. So yeah.
So when you make a wrong prediction, so when, let's say y hat is wrong, when there is no supervision at each step, but when let's say it's actually harmful, then if you consider the reward to be 0, like the question was when is it equal to the NLP? So when the reward is actually 0, then the loss for that is actually 0, which is not the case. The loss will depend upon how far y hat is compared to the true y, like the log of it.
So this is kind of true. I see what you're saying, but let me explain. So basically, it's as simple as looking at the equations. So you can see what maximum likelihood estimation is trying to optimize is this negative log likelihood loss. Or, self-training is trying to optimize this negative likelihood loss. And maximum likelihood estimation is basically optimizing this loss here, where y is instead the correct answer. Basically, if we take this r, and this r is 0, if y hat and y are not equal, then we'll be only optimizing this when log p of y is given axis. So this is the connection between maximum likelihood and reinforcement learning, written in very simple ways. So one problem here is credit assignment. This is a huge problem in reinforcement learning. In fact, it's probably the huge problem in reinforcement learning that makes it more difficult than supervised learning. And basically the problem is, how do we know which action led to a particular reward? So the best scenario is immediate reward, where the moment we take an action, we get a reward. If this is the case, then you know, you might not necessarily know that it was only A2 that caused you to get this reward, but or A4 that caused you to get a penalty. But there's a pretty good chance that the last thing that you did has a high, had a large effect on you getting that reward. So if you can get a reward after each time step or a reward assigned to each time step, it makes learning in this scenario much easier. The worst scenario is this one. So this is the scenario where you get nothing until the very end of your action sequence, and then try to figure out which actions led to this. So the credit assignment problem, if you hear people talking about credit assignment and reinforcement learning, is basically figuring out which of these actions was the one that was actually responsible for this. It's recovering the top sequence from the bottom sequence, essentially. So in the case where we get immediate rewards or we get rewards after we take every action, it's very common to basically assign a decaying reward for future events to take into account the time delay between the action and the reward. So for example, in this case, we might assign a reward of 1 to A2, and then we decay it by half or something, and a reward of 0.5 to A1, for example. And when we do this, normally when we calculate the log likelihood, it's the sum. It's the sum of the log likelihoods for all of our decisions. And in the formula here, I'm multiplying the reward to the outside of this for the whole sequence. But if we can get intermediate rewards, what we do instead is we just multiply these rewards in here, inside the sum. And basically, we multiply the reward for a particular decision. So if we can get intermediate rewards, we just modify our loss function. This way. Yeah.
I must have missed something here, but what if we store all the actions in memory and then we can sift through it once we get a reward to know which actions were least focused?
You still have no idea. So think about your dialogue system that is talking with somebody, and then they say yes. At the very end of your dialogue, they say, yes, this page was helpful to me. There might be somewhere in the middle of the dialogue where your dialogue was actually going really poorly, right? But if you're a computer, and the only thing you get is your yes, no signal at the end, you have no idea that it was going really poorly halfway through. So in reality, your reward should look like 0, -5, -5, -5 when you're doing poorly, and then only at the end you actually get, did well. But you have no idea how bad. You have no idea that that's the case. So it only looks like that with the reward signal at the end. Yeah.
So in retrospect, I mean, once let's say the network was being formed this game,
Yeah.
could we go and interpret the confidence of, I mean, the probabilities of the policy network to understand which was the key choice? I mean, like, for instance, there might be in the game some choices like up and down, which just didn't impact because the ball was somewhere else, and all it did was go one step up, one step down. So that was clearly not a game changer, for instance. So like, could we interpret the probabilities? Let's say the probability was 0.98. That means probably that we need to definitely take an answer. Is there a correlation between like a good move and the confidence?
Is there a correlation between a good move and the confidence? That's entirely model specific, entirely task specific. So if your model is a good model, there's probably a correlation, but 99.9% of the time there will be a correlation. But that can't be guaranteed theoretically. Hang on one second. So one other thing I should note is that in reinforcement learning, or no, maybe I'll note this at the end. I'll get back to this. But basically, there are times when you can do multiple rollouts, which means you try different things for the same data, which is possible for most NLP tasks, except maybe dialogue with humans. And there's ways to use the confidence to choose where you do rollouts and stuff. Yeah.
So I have a question in terms of these fractional rewards
Yeah.
that we have. So for example, given a machine translation task,
Uh-huh.
you're definitely comparing it with individual words in the translated side.
Yeah.
Then how do you decide as to like what fraction of the reward, like a particular immediate step gets assigned?
So yeah, let me write things down to talk about later, because this is another good one. There's a method called reward shaping that allows you to do this, but in general, people don't do this. They just get a reward at the end of the sentence and hope that the network can figure out why it was able to get that reward. So this is not a very effective way of learning, so reward shaping is one good way that you can get around it, and I'll explain that. Okay, any other questions? Okay, so I explained the basics of reinforcement learning, and now the next thing that I would like to explain is stabilizing reinforcement learning. And the reason why stabilizing reinforcement learning is important is because reinforcement learning in NLP, especially if you have a big state space, like your output vocabulary in a sequence-to-sequence model, or 100 part-of-speech tags or something like this, it will never work the first time you implement it. It will break, horribly break, and all your scores will go down to 0. So if you just implement it the way I mentioned here. So there's a lot of tricks to making it work stably that various people and I have accumulated over the years. So let me first cite a couple of problems with it. So as I mentioned last time, reinforcement learning is a sampling-based method. In sampling-based methods, basically what they're doing is they're approximating the space of all the possible actions that you could take. And because of that, they only update with respect to one of the actions or a few of the actions at any one time. So unlike maximum likelihood, they're not able to consider kind of your full state space. And because of this, they tend to be more unstable than other methods you can use. This is particularly true when you have something like all the words in your vocabulary. So using reinforcement learning to do a sequence of 5 decisions is probably fine. You can do it. But if you want to choose over 40,000 words in a vocabulary in your neural machine translation or dialogue model, it becomes very, very difficult. A number of strategies can be used to do this. And the biggest one that you'll see in every reinforcement learning paper in NLP is called a baseline. So the baseline, the idea of a baseline is basically we have an expectation about how well we're going to be doing. So let's do the example of what would be good? Let's say chess or something like that. So let's say you're playing chess against your friend who has not played chess very much before. You expect that maybe you're good at chess, so you're probably going to win. And if you win against them, you might be a little bit happy, but not very happy, right? But if you're playing chess against somebody like Yuri Kasparov, for example, then you have very, very little expectation that you're going to win. And if you win, you'll be extremely, extremely happy, right? So the baseline is basically your expectations about how well you're going to do on a particular thing. So from NLP, let's say we have a 50-word sentence about medical terminology. And we get a blue score let's say we're doing machine translation and we get a blue score of 0.2, and then we have the sentence hello, and we get a blue score of 0.8 or something like that. So if we have a really long sentence about medical terminology, or in the standard reinforce algorithm, basically we will give a bonus of 0.2 for this sentence and a bonus of 0.8 for this sentence. So we'll get better at translating hello not very well, I guess. So what the baseline does is it basically is an estimation of our expectation on how well we do something. And in other words, maybe if we get this really long and difficult sentence, we actually expect that we're not going to do very well on it. We expect we're going to get 0.05. Whereas if we get hello, we expect that we're going to get this right almost all of the time. So if we get it, wrong, we'll be extremely disappointed. So what we do then is we just take the we have an example there. Sorry, it was on my slide. But basically the idea is if we have this is an easy sentence and this is very easy, then and we do poorly on it, then we'll get a negative reward if we take the baseline minus the reward. If we have a difficult sentence and we do better than expected, then we get a positive reward. Are people familiar with the buffalo, buffalo, buffalo sentence? Anybody? A few people. So this is a sentence: buffalo, 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 and it's a proper English sentence. You can look it up on Wikipedia if you want to know what it means. Yeah, you wouldn't expect that you would translate that very well. So this is really what you do in math is basically you take the reward and you subtract the baseline, and that's what you multiply your thing by, your log likelihood loss by. So the log likelihood loss. So if we do better than expected, basically we push in that direction, and if we do worse than expected, we push away from that direction. And this is really important for stabilizing your training. One thing, this is kind of a small pedantic thing, is that you should not be back propagating through your baseline into your model, because if you do this, this breaks things. In DINET, there's the no backprop function. In other frameworks, there's a similar function that you can use to prevent that. Yeah.
How do you use the baseline? Like, what do you use for baseline?
So that's a good question. So let's see. That's my next slide. So the choice of the baseline is entirely arbitrary. You can pick any baseline that you want. The better your baseline is at predicting your expectations, the better baseline it's going to be. So you want it to be as accurate as possible. The one way that people do this is by predicting the final reward using a linear regression from the current state. So there's a couple ways you can do this. One is you take in, if you have an encoder-decoder model, for example, you take in the encoder, you take the final state of the encoder, and then you predict how well you're going to do on the sentence. So the idea here would be if you, after you've encoded, this is an easy sentence, or after you've encoded buffalo, 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 you have a pretty good idea of how well you're going to do when you translate that sentence. So then you just use that to predict your baseline. You can also do it per decoder state. So basically, every state that you have in your decoder, you can predict how well you're going to do at the end of the sentence. So I've seen people do both. Probably this one is more general than the first one, so it might do a little bit better. Another thing that people do is they use the mean of the rewards in a mini batch for your baseline. So if you have, if you're doing mini batch training, you can take the, you you can just take the mean of all the rewards that you get and subtract that. So then the better sentences in your mini batch will get a higher reward, and the worst sentences in your mini batch will get a lower reward. Yeah.
I'm sorry, I'm not catching it really well. Is it from the same model that you calculate the code and then feed it in as?
So, as I said at the very top, the choice of the baseline is completely arbitrary. So you usually have a separate model for your baseline if you're doing something like linear regression. This model can take in hidden states from the encoder that you're using for other things, for example. But you should not backprop into those hidden states from your baseline. This one has no parameters at all, so you don't even need these models.
Do you train your baseline by having the baseline as well as possible?
So the question is, do you train the baseline by having it predict as well as possible? And the answer is yes. Usually you train the baseline with just a root mean squared error, like a standard linear regression model, or maybe an NLP based regression model. Another thing that we found to be really useful recently is if your reward looks sometimes you use reinforcement learning to predict a latent variable like a tree or something. Like this Z here. So you have your reinforcement learning model predict Z from your input, and then based on that you calculate some output, and then you use the log likelihood of the output as your reward for the model. And in this case, we've also found that just conditioning on this without actually using Z or using a model over PY is a pretty good baseline as well. So basically here, this baseline equates to how much are you gaining by having this hidden variable here at Z. So if you're using something like log likelihood as your reward, then this tends to work pretty well as well. Okay. So another trick that can really help you stabilize your training in reinforcement learning is simply increasing the batch size. So the idea is each sample that you get is going to be relatively high variance. It's, it might be good, might be bad, might push you in a good direction, or might push you in a bad direction. So one simple way to fix this is you just do many different examples before you perform an update. Instead of doing your sampling in your backprop over one example, you do 16 examples at a time. And this itself can be useful. Another thing that you can do is you can increase the number of examples. Let's see. Another thing that you can do is you can increase the number of examples for a particular input. So this kind of corresponds to what we were talking about before. So each, when you get an input, you can actually sample a whole bunch of outputs. At the same time for this particular input. And by doing this, this allows you to essentially find ones that are good for this particular input, find ones that are less good for this particular input, and they kind of balance each other out because you're comparing against others. So, when you do this, there's a paper by John Langford, for example, and others, who I don't remember the name, where actually when they do this, they sample up to a point where the model is uncertain, and then they do the rollout from there. So that would be the connection with what you said before. So I think it might be Learning to Search Better Than Your Teacher is the name of the paper, but you'd have to take a look. They have a nice graph in the paper, so you'll know in a moment. Another thing that I haven't seen people use a lot in NLP, but it's used more in kind of classical reinforcement learning tasks like games, is you can save your previous rollouts and then reuse them when you go and update parameters. And this is called experience replay. And the idea behind this is basically that you've already you have examples from a slightly different version of your policy, and you want to make sure that you're not making those worse. So you go back and revisit the things that you've already done at one point. This is particularly useful when calculating your rollouts is very expensive, but maybe calculating the parameter updates on the rollouts is not very expensive. So let's say you're doing a big search over all of your possible things, like options to do a rollout. So a good example of this is AlphaGo, where AlphaGo to play a game takes a lot of time. So you play a lot of games and then you go back and revisit the games that you've already played. Okay. So worm start is another thing that you can do. This is exactly what I talked about before. Or last class. So you start training with maximum likelihood, and then you can switch over to reinforce. So this only works in scenarios where you can run maximum likelihood. So you can't do it when you have latent variables that you have no chance of observing. That being said, there are a lot of scenarios where, let's say you have annotated parse trees or something like that for a small amount of your data, but then you want to do semi-supervised learning on a large amount of the other data. So then you can do supervised training on the small annotated data, and then semi-supervised training on the data where you don't have those annotations. Yeah.
So, in the context of like a game when you need label groups, how do you do that?
Yes. So actually, the first AlphaGo, the first iteration of AlphaGo, or actually until very recently, AlphaGo was doing this, where they learned directly from human expert games first, and then they transitioned over to doing reinforcement learning to learn how to play even better than experts. In the NLP sense, it would be, like let's say you have parse trees for some portion of your data, but you don't have it for others because labeling parse trees is expensive. So. Yeah.
If you start with something that you're feeling over does it not bias the model?
If you worm start with something trained on MLE, does it bias the model? And the answer is yes, it definitely does. If it wasn't biasing the model in some direction, then it would have no effect. The question is whether it's biasing the model in a bad direction, and my guess is the answer is probably still yes. So if we could do reinforcement learning really, really well, we would probably find a better answer, but we can't do reinforcement learning really, really well. So because of this, this is usually a very good option. So, yeah. Anything else? Okay. So let me get to when to use reinforcement learning. So reinforcement learning is very popular nowadays. So I've had a lot of people say, I want to use reinforcement learning for this, when actually there's a much easier way to solve this. So there's a very obvious, or let's see. So if you're in a setting where the correct actions are not given, and the structure of the computation depends on the choices that you make. So, so let's say we're in a situation like the example I gave before, where we have a parse tree that we want to create, and then based on that parse tree, continue something else. Or let's say we're in a dialogue system where the dialogue system needs to look up stuff on the web based on some actions, or do or return weather information based on other actions it chooses. If this is the case, then reinforcement learning, yes, is a very good option. In fact, it's probably the only option that you have. So in the dialogue system scenario that I talked about before, there's no other way to solve this than reinforcement learning. if you're in a setting where correct actions are not given, but the computation structure doesn't change, in other words, let's say we have a recurrent let's say we have a recurrent neural network that outputs a sentence, a recurrent neural network that outputs a sentence, which is then fed into a question answering system that outputs your answer. You have a black box question answering system, so you don't know for sure if the like how it works or anything like that. So in this case, you'll be doing something like feeding, like predicting a word A, feeding that word A back in, predicting word B, feeding the word B back in, etc. But even if you choose a different word, even if you choose D here, you'll still have the same shape of your computation, basically. So if this is the case, there's actually other methods to solve this problem that don't require reinforcement learning or making discrete decisions. So there are differentiable approximations to this. One example of this is the Gumbel softmax, which I'm going to be talking about later. So if this is the case, you don't necessarily need reinforcement learning, and there are other ways that tend to be more stable. So I'll talk about these in a little bit. So yeah, another thing you could use is like scheduled sampling or reward augmented maximum likelihood, the other simple things that I talked about last time. If you can train using MLE, maximum likelihood estimation, but you want to use a non-decomposable loss function, so something like BLUE score that doesn't decompose well over the sentence. You might want to use reinforcement learning, but there's also lots and lots of other methods that you can use, and some of these methods tend to be more stable as well. And some of them I've already talked about, like the max margin type methods. Some of them I'll be talking about. So are there any questions so far? Does anyone have a problem where they want me to tell them if they should use reinforcement learning or not? Okay. No? Okay. I'll be happy to tell you individually later if you want to know as well. Okay, so an alternative view to policy-based reinforcement learning, there's also value-based reinforcement learning. So these are different in that policy-based reinforcement learning, which I just talked about, is trying to learn a good probabilistic policy that maximizes the expectation of the reward. On the other hand, value-based reinforcement learning is trying to guess the value that will result of taking a particular action. So in other words, given this action, what do I expect my reward is going to be? And then once you do this, you return the action with the highest expected value. So this action value function basically looks like, given a state S, we try to estimate the value of each action A, where the value is the expected reward, given that we take that action from this state. So R actually is a subscript of R, or within R, I probably should have had ST also. But given that we take this action at the state, what is the expectation? So in an example, in a sequence-to-sequence model, our state would be the input and the previously generated words, and the action would be the next word to generate. Yeah. So then we take argmax of this function. So one thing to note is this doesn't necessarily have to be a probabilistic model. There's no probability anywhere in these equations, but except maybe in the expectation, and the expectation can also be defined in other ways if you wish. So how do we estimate the value function? So how many people have implemented Q-learning or tabular Q-learning before for something? Okay, that's actually fewer than I thought. In my undergrad machine learning class, I implemented tabular Q-learning for a taxi driver who was driving around and would drive off cliffs if you went in the wrong direction. But anyway, so tabular Q-learning basically, in this case, you can explicitly remember this Q function for each, or you can explicitly remember the expected reward for being in a particular state. So if this is the case, you just have a table of all of your states. You have a table of all of your states and action pairs, and then you just remember the last time I did this, how much reward did I get when taking this action in this state. And then this time when you took the action in this state, you update the Q value by a little bit based on the reward that you got this time. So every time you have basically a rolling average of this. So R is the reward that you got this time, and Q is the value that you estimated the previous time. So the problem is we can't remember all of our states. So if we think about a sequence-to-sequence model, basically our states are the input sentence and all the words we've generated so far in the output sentence. And that's exponential in size. We'll never see all of them, and that doesn't scale. So it only scales if you're doing something simple like tic-tac-toe or something like that. So instead, what you do basically is you perform regression on this Q function where you take in your state and your action, some representation of your state and your action, and you try to predict what your Q value would be. And actually these neural Q function approximators were maybe one of the first really big high-profile successes in reinforcement learning. Does anyone know what the Tesoro was? Backgammon, yes. So this was a neural reinforcement learning agent that basically won at backgammon, which is a pretty difficult game because it has chance and incomplete information and stuff like that. So it was the AlphaGo of 1995, and then there was what else? Deep Blue that beat Gary Kasparov, and then there's AlphaGo now. So another really important point in reinforcement learning is not only in value-based reinforcement learning, also in policy-based reinforcement learning, but particularly in value-based reinforcement learning, is that you need to do exploration versus exploitation. So the problem is if you always take the best current option, you run a really high risk of landing in a local minimum somewhere. So once you've eaten a McDonald's hamburger and it kept you alive, which means the reward was more than 0, then you will continue eating McDonald's hamburgers for the rest of your life, which doesn't sound like a very good idea, right? So now my daughter tries to eat everything, and that's because she's doing her exploration right now. And then she'll probably stop eating everything pretty soon and start exploiting the things she likes. So basically, this is less of a problem with stochastic policy-based methods as we randomly sample actions, and the Q1 is just taking the argmax. But what we do in Q, in kind of the value-based reinforcement learning, the simplest strategy is called the epsilon greedy strategy. And basically what we do is we have some probability epsilon, and we pick a random action with this probability epsilon. And then there's, and with a probability 1 minus epsilon, we take the best action that we know at the time. So this allows us to kind of get off the path of all the things we've seen before. If epsilon equals 0.1, then 1/10 of the time you'll eat something other than a McDonald's hamburger. And you'll realize that there are better things in the There's also a lot of other interesting things in this, and actually I haven't written all of them on the slide. I probably should write a few, explain a few more. But one interesting one is intrinsic reward. And so basically what intrinsic reward is saying once you've discovered something that looks kind of new, once you've discovered a new state, you get a reward for discovering that new state. And the idea here is you want to explore and try new things that you've never done before. And every time you try a new thing, you get a reward for trying a new thing. So this kind of makes a lot of sense, right? And then the problem becomes how do you define that you've done a new thing? How do you define novelty in a non-trivial state space? But that's another thing that you could, it's another thing that you can do with neural networks. When you get a representation close to one that you've never seen before, then that might be a new thing. Some other things that people do that I should mention here. One thing that people do, especially in stochastic policy type methods where you make random decisions, is in addition to your reinforcement loss, so let's say we have our reinforced loss here. We also have a loss that basically measures the negative entropy of our decisions. So, if you remember, the entropy function is basically a measure of how uncertain you are about your decisions. So if you have a really peaky distribution that says, okay, I'm really confident that I should be making this decision, then this will have a very low entropy, right? But if you have a non-peaky distribution that gives approximately equal probability to a bunch of different decisions, then the entropy will be high. So you want to avoid low entropy decisions because this means you're not exploring enough and encourage high entropy decisions. So you subtract the entropy from your loss function. So one kind of annoying thing about this is you can get a negative loss because now you're subtracting something that tends to be positive, but in practice that's not a problem. So in the last couple minutes, I would like to talk about a few examples. Are there any questions up until now? No? Okay. So the one place where reinforcement learning has been used forever in NLP is Dialog. So there's a reason why I gave that as a very good example because reinforcement learning is a very natural fit for Dialog. You don't get a reward until the end. You don't know which Dialog turns were the ones that actually helped you out. So there's a good survey by Young et al. In 2013. This is on partially observed Markov decision process models. This was done before everything became neural. So obviously it doesn't have this, but it can give you references going back 20 years on this. Now the obvious thing to do is to apply all our reinforcement learning techniques that we have for neural methods to Dialog as well. So there are also neural network models for task-based and kind of chatbot-based dialogue. And most of these are using the kind of standard reinforce machinery with a few tricks that I talked about. One thing that Dialog people have done really well that surprisingly people aren't really using very much in neural dialogue, or as far as I know, maybe things have changed in the past 6 months or something. But it wouldn't be unheard of. But in previous systems for Dialog, what people would do is they would build user simulators. And user simulators are basically simulation tools that generate a huge amount of data automatically that kind of simulate your users. So what you do is you create a simulator that has an internal state. And this internal state is not observable to your system. Your system can only see how that user simulator acts and what utterance it gives. And the Dialog system must learn basically to track the user state without actually ever being able to observe it. So one example of this is basically here we have a user with a state CO, I guess, which is it's what the user wants, and then based on that, the user simulator generates, I'm looking for a nice bar serving beer. And then the system says, okay, a wine bar, what price range? Making a mistake, obviously, and then based on this, it will get a low reward at the end of the dialogue. So then the system will be able to update its parameters. And you can also add things like speech recognition noise or whatever else into these user simulators as well to make sure they're robust, et cetera. So this has been really successful. If you're making a dialogue system and you want it to work, this would be a very good way to start. Another place, this is one of my favorite undercited papers in NLP, I guess, or underappreciated papers in NLP. So this was another thing, another reinforcement learning paper that's not neural, but is doing something very interesting. So what the idea is that you follow Windows commands with weak supervision based on progress. So basically, it learns to read the Windows manual. So you have a Windows manual that says, first do this, then do this, then do this, then do this. And its reward signal is based on whether the words in the next instruction appear on the screen. So the idea is if you do the correct action, you'll probably get some words from the next instruction on your screen. If you do the incorrect action, you won't advance in the proper way, so you won't get this. And I think they also applied this to playing Minecraft or some other StarCraft or something like that, one of the games. Maybe Minecraft. Now people, of course, are applying this to neural net type models as well with visual instructions and other things. But I think the basic idea is another place where reinforcement learning is very widely used is when you're making, So reinforcement learning, is very widely used to tune machine translation systems. And basically what you do is you output a translation. Based on that translation, you get a reward. And then you get that, then based on that reward, you update your parameters, et cetera. As I said, that's not really a scenario where you really need reinforcement learning. There's a lot of other options there. As one example where you do need reinforcement learning, this is something I'm very interested in. This is a field I'm very interested in, and it also happens to be one where I wrote a paper in, so I'll talk about my paper. But the basic idea is, in sequence models, usually you read in the whole input sentence before you start generating them. But in the case of for example, a speech translation system, you might not want to wait for me to finish one of my very long-winded sentences that goes on for 60 words before you start getting a translation. So the idea here is basically you want your machine translation system to start translating as soon as possible once it's seen enough input to be able to translate. So we have a little reinforcement learning agent with only 2 actions. One action is read and one action is write. So it basically decides whether it wants to read in more input before it writes. And the reward signal here is a combination of how quickly you translate and how well you translate. So then you can adjust the weighting factor of each one to get better translations where you wait longer or faster translations. There's also work in reinforcement learning for information retrieval. So this is another really cool idea where basically, sorry, I wrote information retrieval, but it should be information extraction. So the idea is you want to do information extraction from newspapers. And when you get a newspaper article, what it looks like is you want to extract, for example, information from an article about a crime incident where somebody was murdered, or people were murdered. And the shooter name is one thing that you want to extract. The number of people killed is another thing that you want people to extract. It's a very morbid task, I guess. And then in the article that you're given, you have a couple and 4 children found dead in their burning South Dakota home, had been shot in a murder-suicide. And a couple and 4 children is kind of difficult for your computer to understand, right? So basically what it does is it does what everybody else would do. It just Googles and tries to find the answer in another news article that's more direct. So it says the 6 members of a South Dakota family found dead in the ruins of their burned home were fatally shot or something. So then where reinforcement learning comes in is now you have to make a discrete decision where the structure of your computation changes based on whether you decide to Google or not. So it uses reinforcement learning to update the parameters in this case. There's other more recent work where you do query reformulation, which is basically where you change a different, you create a different query based on search query and restructure it in the appropriate way based on the whether you get good results or not. Let's see. Okay. Yeah, I have two more slides. So one more is course-defined question answering. So this is another good example where you really need to use reinforcement learning because the structure of your computation changes based on what you choose. And the idea here is that you have a big document where calculating or big document collection, where calculating your recurrent neural network over the entire document collection would be, prohibitively expensive. So the idea is you have a really fast model that basically you have a really fast model that can browse the sentences and then pick the ones that are salient to what you want to be doing. And then you have a model that creates a document summary, and then based on that summary, you generate an answer. This summary is latent, of course, so you need to optimize with respect to this to get the best summary possible in your summarization. Yeah.
In what sense does the computation structure change here? Let's say if you're picking a fixed number of sentences or something.
You're not picking a fixed number of sentences, and they're also not fixed length, for example. Any other questions? Yeah.
In the previous task and the task before that, basically there's kind of a trade-off between optimizing for time, in a sense, and optimizing for accuracy. How do you usually go about designing those reward structure?
So that's a really good question. So the short answer is there's really no correct answer, I guess. For this particular task, we actually did a different thing where we did a human study to see which one humans prefer more. So you could certainly do that, but that's a lot of work. Another thing that people often do in these kind of multi-objective optimization scenarios is say, we have a bunch of choices. One, where it's like one choice is fast and one choice is accurate. And we have a bunch of systems like this. And basically we want kind of ones on the upper boundary here. All of these ones are worse at everything than one of the other systems, so you don't care. And you just want one up here, and we're not going to, decide what trade-off is better, or we're not going to decide how to trade off. And these systems are called Pareto optimal, or these are maybe strongly Pareto optimal, and this one is weakly Pareto optimal, or something like that. But either you explicitly try to make the decision based on some value, value decision, or you just say any of the ones that are on this Pareto frontier are fine. Any other questions? Okay, so there's also work on using reinforcement learning to learn network structures, for example. So basically the idea is you generate a neural network structure, try it, and measure how well it does as the reward. So this is not necessarily limited to NLP, but we all know LSTMs now, and LSTMs have this crazy network structure. And this can learn an even more crazy network structure where you have a whole bunch of like CAN-H. I don't know why it has all these identity nodes in there. That doesn't seem very optimal. But anyway, it can learn this crazy network structure that does better on some tasks. And there's a lot of work in this area right now. It's often called meta learning. It's also called architecture search. So if people are interested in this, you can take a look. Yes, so that is all for today. Are there any questions? Yeah.
What sort of tasks would probably use to evaluate?
What sort of tasks?
What sort of tasks would you probably use to evaluate what are you learning?
We can use any task that you're interested in. I think if you're trying to learn network structures, probably the answer is you want to evaluate on ones that people care about, and probably it's best to show that your network structure works on lots of different tasks. But that might not be the case. There might be an ideal network structure for each task, so it's not.
The architecture that are done, aren't they preliminary? Like, is there any understandable why is it doing that?
As far as I know, I don't know. Do you have an answer? Does architectural search learn intuitive network?
It's not intuitive at all.
It's not intuitive at all. Is the answer from the experts. Okay. But did you have questions? Yeah.
When might you pick like value versus like policy?
Oh, when would you pick value-based reinforcement learning versus policy-based reinforcement learning? That's a good question. I guess recently it's very, very common to use policy-based because policy-based is simpler usually. That being said, there are a few really nice kind of intuitive advantages of value-based reinforcement learning in that, for example, you can have there are things called actor-critic methods where you have one network that tries to decide what to do, and then you have another network that looks into the future and says, this is what you should actually be doing. And kind of intuitively, I like that idea. That being said, it's probably largely an empirical question, both with regards to how well it works in terms of accuracy, how fast it is, and how easy it is to implement. And from that point of view, I think that the latter two, easy to implement and fast, usually policy-based methods are better, and the gain that you get from value-based methods in NLP anyway has not been large enough that people have been encouraged to use policy-based. But if you were the one to change that answer, then that would be another very good contribution. So, yeah, I don't know. Any questions? Okay, thanks a lot, everyone.